Okay, we should be live. Welcome to another live stream session on the assumptions of physics, a research project. Today we have a guest that sort of joined the discussion last week, and we're trying to go into some details of essentially which, let's say, category is more appropriate for the type of things that we have been doing in terms of experimental verifiability. I've been strictly in just using topological spaces because that's what I know. There are three things that are sort of similar, the locale, the frames, the hiding algebras. I know that what I have is a hiding algebra. I do not understand in the category in the categorical framework how these three things are different. I was told by somebody who knew more than me that the morphisms are different, but I also didn't know exactly. So if Brandon can clarify these details for us, that would be great. So please.
All right. Yeah, thanks for having me. I guess the first thing I just wanted to say is that this is, I think, a question about language and terminology. And so I've read through the first couple chapters of the physical mathematics book, and math seems to be correct and everything seems to stand for itself. But that said, I think having kind of a categorical perspective on things can sometimes just offer a different way of thinking about things.
Mhm.
So yeah, I can jump into some definitions. Um, so I'll just start with frame and complete Heyting algebra. So a frame is a poset. Um, it has arbitrary joins and finite meets and a distributive law. Just saying that they interact well with each other. Um, so the canonical example of this is open sets of a topological space, of course. Um, and then a complete Heyting algebra is a poset. It has arbitrary joins. And instead of finite meets, it now has arbitrary meets.
Okay.
And it also has a distributive law. Um, but it also has two, well, I guess one additional new thing, which is implication, which is a binary operation on the elements. It also has negation, which is a unary operation, but negation is just defined as X implies false.
X implies false.
Yeah, the bottom element.
Oh, because this is where the implication is actually an operation on the lattice. Okay,
Yeah,
yes.
exactly. So there's, the less than or equal from the post set. And
Yeah.
then this is kind of capturing the, largest statement that kind of captures the less than or equal to relationship. Um, so we'll go into a little bit more detail, but just pointing out that this has some additional structure. It has the arbitrary meets and the implication and negation.
So does that mean that not all frames are complete hiding algebras then?
Uh, so uh, so it's clear that every complete Heyting algebra is a frame.
Right.
Less obviously, the reverse is true.
Ah, the reverse is true. Okay.
Yeah, every frame is a complete Heyting algebra.
So then the arbitrary meet, then if I were in a topological space, it would not correspond to arbitrary intersection then.
Correct.
Okay.
Because you define the arbitrary meet as you know, the largest element that is smaller than all the elements xi. So it's
Okay.
all the y such that y is less than xi for all I. So it's really the interior of the of the meet.
Ah, okay. It's the interior of the intersection. That's
Yeah.
the
And then also just write the definitions for the other two things. So sorry, so this is if you're taking a frame and you're trying to induce the structure to get the complete Heyting algebra, that is the largest z such that x and z implies y.
okay.
And I'll just point out this particular case of not the negation. That is the largest element that is inconsistent with,
Right.
yeah.
That is the exactly.
Yeah, this is in the book, you define this as the falsifiable part of X. So it's basically the interior of the complement.
Yeah, exactly. It's interior of the complement. It's the exterior. Yes.
Yeah. Um, so yeah, I think just the point that you've already kind of nailed on is that this is not equal to the intersection or the, logical,
Yeah.
yeah.
So this reminds me of sort of the inverse of the intersection structure, right? So the intersection structure is where you can always make the intersection, and you use that as a meet, and then you use the join by basically doing a procedure, but with the order reversed, right?
Yeah.
Okay, good.
So yeah, I think really the critical thing is that these are like for finite meat, you do have the same thing as logical conjunction. For arbitrary meat, it stops being equal.
Right. And the
Um,
thing is that I need to keep track of both because I want to be able to say I have the negation and I have the falsifiable part, and I want to be able to talk about the two things separately so that I can get intuition.
yeah. So the notation that I'm probably a little bit most comfortable with in this context is the meat is going to be the actual meat, but then you can write like intersection if you want the intersection and
Yeah.
complement if you want the complement.
That's fine. I'm able to translate. I had to get used to so many notations, and whenever somebody says, "Oh, you're not using the right notation," I mean, there are like, yeah, 10 books have at least five different notations. Okay, very good.
Okay.
So
So
these two things then, at least as objects, they are the same things because you can go from one to the other.
yeah. Although one thing I want to point out is that this equivalence, I think of it as almost an accident. Uh,
Mm.
and it's because you're using this join that is going over all elements that are less than something. So essentially, this is a very large join. This is a join over basically the size of the universe, if you consider the lattice to be the universe.
Right.
So um, for example, one thing I was thinking about with this project was sigma frames. So sigma frames, you have only countable joins instead of arbitrary joins.
Right.
Now, we kind of avoid that issue because we assume second countability. So there's a countable basis. So it actually is a frame. But if you were working with sigma frames, you would run into an issue because the join that you want to take here is
Yeah.
larger than you have access to.
Yeah.
Okay. Um, and then, oh yeah, I should also just mention that this implication operation for topological spaces is just so in topological spaces, this is the same thing as not x or y.
Uh, yes, which is the standard way that one does the implication.
Yeah, and it's not true in all Heyting algebras, um, because you can have kind of like more non-classical logic structures. This is actually derived from the fact that points, that topological spaces have points that define open sets,
Right.
and points are either in an open set or not in an open set. So you kind of get the classical logic coming in from that.
Right.
Um,
So
yeah,
let me get this question. So suppose that I have, okay, is every frame a topological space? Then the answer, I guess, is no.
Every frame can be so what I'm going to do is we start with frame, which is an algebraic structure.
Hmm.
We flip it, we flip the morphisms to get locales, which is we should think of it as a geometric structure, a space. Every locale can be turned into a topological space and vice versa. And the question is when are those operations inverses of each other?
Okay.
And so I kind of want to get into that, but
Okay.
first I want to like rule out complete Heyting algebras as the basic structure that we want to think about.
Okay.
So I want to get into the morphisms. Because like you said, it is a question of morphisms.
Good.
So
So I did understand some things. Good.
and specifically it's because, in category theory, the morphisms are really defining what the structure is.
Yeah.
And in this case, we've written arbitrary meat in the definition, so it ought to be preserved by the morphisms. So
Right.
complete Heyting algebra morphism preserves, a frame homomorphism has to preserve the less than or equal to, the arbitrary joins, finite meets. The complete Heyting algebra homomorphism, in addition, has to preserve arbitrary meets
Right.
and the implication. Um, so I just want to give one example which I think, this might be enough to just rule it out as the basic object, but essentially, if you have a map like um, f from R to R, which takes x to maximum of x and 0. So this is just this graph. Um, so this to me, like, I think there's maybe a physical situation where this would occur, like if you are taking the temperature of something and your thermometer has like lower and upper bounds on what ranges of temperatures it can display, then you're essentially just truncating a range of possibilities. So this seems like physically
Yeah.
justified. You would want this sort of.
Basically, every continuous function is gonna be good, and that's a continuous function. So yeah.
Yeah. So I want to show that this does not preserve negation. So if you take
Okay.
an open set like let's call it in the codomain, you take an open set like y. What do I want to use? Y is greater than 0. Um, the negation of this is just y is less than 0. Then stop me if at any point there's something that isn't clear.
Hmm.
But f inverse of that, well, it's a non-negative function, so this is just the empty set.
Yeah.
Um, versus if you take f inverse, you get
Hmm.
x is greater than 0 because x is greater than 0 if and only if y is greater than 0. And then you take the negation of this and you get x is less than 0.
This is just a minor thing. You excluded 0, right?
Yeah.
Yeah, I excluded so like when I do the negation operations, I'm always changing greater than to less than because it should be, excuse me, the exterior. So it should be the interior of the complement, which would exclude 0.
I see. Okay.
Y less than or equal to 0 is not verifiable.
Yeah.
All right. And if you sit and think about what went wrong with this example, it
So
essentially comes down
wait,
to,
before proceeding, so exactly the negation is not preserved because let's see, we went from I'm trying to think. So the negation because it's not the exterior of the other one. Right? That's basically the idea, right?
yeah. So so it's essentially the problem at its core is because you can take a verifiable statement in the domain, x is less than 0,
Yep.
and then take the image of that,
Yeah.
and you get just y equals 0.
Right.
This is no longer a verifiable statement.
Right.
So that maybe hints at what a complete Heyting algebra homomorphism corresponds to topologically. But we'll write that down explicitly as well.
Okay.
So, yeah, so then just a question, suppose you have a continuous map between topological spaces. It's a category of topological spaces. When is F inverse? Because we're always dealing with the inverse image function. When is that a frame homomorphism? Always. Because for finite meets and arbitrary joins, those correspond to intersection and union, and F inverse always preserves union and intersection. When is it a complete Heyting algebra homomorphism? So I could not find this in the literature. So I spent some time trying to work it out. I was able to figure it out for T1 spaces. So if Y is T1, then this is if and only if F is open.
Oh, okay.
For general spaces, it seems to be, it could also just be that it's open, but it might be a little bit weaker. Open implies that it's a complete Heyting algebra homomorphism always.
Okay.
But it's something about being open. And for when Y is T1, it is exactly when it's open. And there is a reason that topological spaces are defined with continuous maps, not open maps, and it's because continuous maps are useful even if they're not open.
Yeah.
And the category of topological spaces is better behaved than the category of topological spaces with only open maps.
Right.
For example, I
Yeah.
don't.
Is there like some properties that sort of break down otherwise?
Yeah, so I read that I haven't worked this on myself. I read that it doesn't have products even. So it's not going to have limits, not going to have colimits.
Oh, wow.
I don't know about colimits. It at least doesn't have limits.
Okay. Interesting. Okay, so but yeah, from my perspective, we show that the continuous map are the things that we want. So
Yeah,
so I have a principal way, but it's always nice to see when the principal way to get it gets you that structure that then also mathematically is nice, and then
yeah,
that's the thing
yeah,
that
exactly.
yeah.
Yeah, so if we're ready, I can move on to locales.
I'm fine. If people have questions, I want to go slower, do tell me. I there is the chat, so put people question in the chat, and Mark and Tobias, if you want to interject, please do.
I'm fine.
Yeah, I like the pace. It's fine.
Good. Let's go. Let's continue then. This
All
is
right.
this is so useful. Thank you so much for coming on because yeah,
Yeah.
these are the things that it's so difficult to just understand from the outside because you would have to read like it's like 600 pages to actually read the two paragraphs that you're interested in
Yeah, exactly.
yeah. So thank you so much. Go ahead.
Yeah. I guess I should mention this is all pretty like, well, apparently not this specific question, but everything else is pretty like established in the literature. Like
Yes.
it'll be easy to find like resources once you have this terminology and generalizations and theorems, all that. So if you look up the definition of a locale, you're
Yep.
going to see that a locale is a frame. You're going to see basically that locale, the category of locales, is the opposite of the category of frames. So that
Opposite. What does that mean?
this basically just means if you have a category, so you have your objects and your morphisms.
Oh, you switch the arrows.
Keep the same objects, flip the morphisms. So it's literally like what is a morphism of frames? Or sorry, what is a morphism of locales? It is exactly a morphism of frames in the reverse direction.
Okay.
But that I think trivializes it a little bit. Like, why would you even define locales if it's just the opposite? But really, it's because there's a different intuition for these objects. So frames should be thought of as algebraic objects. basically lattices. So if you're thinking of your verifiable statements as a set in isolation, you would probably think of it as a frame. Locales should be thought of as geometric objects, very similar to topological spaces. And this is in math, we say that like geometry is dual to algebra. This is a very trivial example of that when you have a geometric category that's exactly the opposite of a
So what makes it geometric instead of algebraic? I not following.
Yeah. So it's essentially the relationship to topological spaces.
Okay.
And like if we start working through it, you'll see that there's a lot of like similarities between the two categories of locales and topological spaces. And we can make that precise. But if you have a continuous map between topological spaces, you can break this up into two pieces. You break it up into a function on points.
Yep.
And that's covariant, meaning that the arrow goes in the same direction.
Or in
And
the fashion of the open sets. Okay, good.
yeah, and the open sets, which is covariant.
Okay.
Using F start here, which I'll explain in a second, which is contravariant. And the same is true for locales. So if you have, I guess I can stay here. If you have a locale, then the open sets of a locale, you think of it as just the corresponding frame.
Mhm.
And the points, I'll define in a second, but you can define points on a locale. I think you might say that locales are topological spaces without points. Well, they actually do have points. And if you have a morphism between locales, you can turn that into a morphism between points, or a function between points, I should say. And so this kind of analogy with topological spaces is kind of why you would want to think of them as spaces and not algebraic objects. So yeah, so what are points, I guess? So points of a locale, it's the same thing as, like, if you think about the category of topological spaces, how would you determine the point of a topological space? Like, one way to do that categorically is to take a morphism from the singleton space into the space. So one is the singleton space, which is a single point and two open sets, just empty in the space itself. And what is a continuous map from the singleton space into a topological space? It just picks out a single point.
Okay.
So you can recover the points of a topological space using morphisms.
And the point is that there is one such map for each point, right?
Each point,
Yeah.
yeah.
For a topological space, you can recover the structure of the set of points using category theory, using the morphisms. And the same is going to be true for locales. But locales don't have points in their definition, so we're not really recovering something. We're more defining what a point is of a locale. It's exactly a morphism of locales from 1 to x. And these are locale morphisms, or locale morphisms rather, which are the same thing as frame morphisms from x to it's going to be the open sets of one, or I should just be careful with the notation, from the open sets of x to the open sets of 1. What are the open sets of 1? Well, they're just
The full, yeah. The top and bottom.
yeah, the truth values. And so this is basically saying, for like topological spaces, the way you would think about this map is it takes an open set and just returns true if the point is in that open set, or false if it's not. So it's like deciding for each open set, am I in this, am I not in this? Um, and um, so I am now talking about locales specifically, not about topological spaces. You sometimes have that these are equivalent to each other in topological spaces, but not always. I'll get to that in a second.
Okay.
But for locales, we just define a point to be this. By definition, that is this.
Yeah, so remember, like I tried multiple times to go and study category theory by myself, and then I always arrive to a point that I don't understand anything. But I remember that in the category of set, you do something similar to get to retrieve the elements of the
Yeah,
set, right? Yeah.
exactly. That's kind of the, one of the points of category theory is that you can recover structure using morphisms, all of the like intrinsic structure, which is in the definition of the object. You can kind of just forget about that after you define morphisms, because morphisms allow you to recover structure.
Yeah.
But is this clear so far? I can definitely.
Yeah. To me, it's absolutely clear. I don't know if it's clear to everybody else. As I said, this is super useful for me. Also because we are very terse. We are only saying the important things and nothing else. So for me, it's perfect.
Yeah, that makes sense so far.
Okay.
Okay.
Didn't forget what do you mean by reversing the arrows? Like I see now it's a map that goes in the other direction, but like do I take like all the morphisms and then the inverses? They don't need to be invertible. I don't.
Right. So that's a good question. The thing to know is that in category theory, we draw arrows. So a category is, objects, and then you define what a morphism between objects is. So, but they don't actually have to correspond with functions. They don't have to correspond with transformations. In category theory, you can define the arrows to be whatever you want. So categories are very general structures. And so actually when I like in frames, when I draw an arrow between two frames, it actually is a function. It's a function that takes in a frame and it takes in elements of one frame and returns elements of the other frame. For the category of locales, an arrow from X to Y is actually a function from elements of Y to elements of X.
Okay, so can I really think of it like as a list of points and then arrows between them, which kind of tell me I can go from one point to the other point via some morphism? Now I just really flip them.
Once you've defined a point to be a morphism from 1 to X.
No, I think he means point as object in the category.
Yeah, sorry.
Oh yeah, sorry. So yeah, I would say X is an object. You can compose morphisms. So you can, in that sense, you can think of them as like being adjacent to one another. But just the existence of this opposite operation where you like just flip all the morphisms, you just define that a morphism from X to Y is actually what we previously called a morphism from Y to X. Just the existence of that operation kind of implies that these things are not really directional, even though we write them directionally. It's just that you can only, it really defines the way that you can compose these objects. So you can, if you have X to Y and then Y to Z, you can compose those.
So to your question, yes, a category is just a list of objects, and then the morphism is just pairs. That's it.
Yeah, exactly.
So also a morphism is really just defined by from what the 2 points it connects. Like in the picture above, or no?
So like if I'm writing down the definition of a category, what I'll say is this. I'll say like it's kind of similar to like how you define a topological space. You say, okay, what are the objects of my category? And so I'll just write like a set, like I could list the objects or define them in some way. Then I would say, okay, well, what is given X and Y that are objects of C, a morphism, the set of morphisms from X to Y is defined as, right? So then I list out all the morphisms between X and Y. And then I also have to define composition.
Yeah, but then really, all I know is like what kind of morphisms do I have in the sense of which objects have an arrow and which don't have one.
Exactly.
Okay. Yeah,
So
that
in
makes
category
sense.
theory, all properties are defined just in these like abstract like diagrams of arrows. And I'll say like yeah, you can define all kinds of constructions, but it's all just defined in terms of these arrows. Like, is there an arrow? Is there not an arrow?
Yeah. And you can say you basically
Okay.
just have you can have multiple arrows between the same 2 points.
Yeah.
Yeah. Okay.
And I think composition is a thing, right? Like if you have an arrow from X to Y and one from Y to Z, then you definitely also have one from X to Z.
And you always have identity morphism from an object to the
Yeah.
side.
Yeah, that makes sense. Thanks.
Okay. And so one thing I like about defining points as morphisms from 1 to X is that if you have a continuous map or a morphism from X to Y, then you can actually recover its action on points. Like if you have a point of X, then you just compose it with F and you get the point of Y that is the corresponding point. So just a neat thing. And actually, this also works for open sets. So you can recover the open sets of a space. This time you actually are recovering it because it was part of the definition as maps from X to a special space called Sierpinski space. Sierpinski space is, it has as points, it has 2 points. What should I call them? Maybe just 0 and 1. And the open sets of the Sierpinski space are, of course, the empty set, the set containing 1, and the set itself. So we should think of the Sierpinski space as like the set of truth values of a statement, maybe, or maybe the set of outcomes of an experiment. But basically, like there are 2 possible outcomes, 0 and 1, but only 1 is verifiable. You can only verify that you've got the value 1. And so if we're thinking of F as like a transformation of something or something from X to another space, then it basically takes every element of X, every point of X, rather, and returns 0 or 1. So, yeah, so let's say we have like a statement S.
Yeah, it's basically a statement that tells, am I in this open set or not?
Yeah, exactly. So if you have a statement S, then you just associate that with the map that takes X, the point X to, is, well, 1 if X is in S and 0 otherwise.
Yeah.
And so, yeah, so basically to say that it's a verifiable statement is kind of just to say that it's a map into this space which has 0 and 1 where only 1 is verifiable. It's kind of just the definition of verifiable. It's a little trivial.
Yeah, so it's basically a different way to reorganize everything, but you're laying down exactly how the thing is reorganized so that so that we can understand the maps between the different ways of looking at it.
Just like this is just like the categorical way of thinking about these things is that you have like, instead of thinking of X as having this intrinsic structure that is like part of its definition, you look inside the objects to get the structure. This is a way of getting that structure from the outside by looking at how it interacts with other objects. And you can do the same thing if you have, a morphism from X to Y, and a statement on Y, or an open set on Y, then you can compose that to get F star of S, or F inverse of S. Okay, so anyway, this was all to say that, like, really the whole point of that whole thing was that given you define locales in terms of their open sets, but then it is possible to define points for locales as well. And so that suggests that you can go from a locale to a topological space. So specifically, if you start with a topological space, so this is the category of topological spaces. This is the category of locales. You can, let me just make sure I write this in the way I like it. Yeah, so you can go from topological spaces to locales just by forgetting that you have points.
Right.
And you can go in the reverse direction. And that is just by defining points as maps from 1 to X.
And now the question is, can I always do it?
Right. So you can always do it. Like, you can always, any topological space can be turned into a locale. Any locale can be turned into a topological space.
But do I
Problem is that they
land
are
in the same
inverses.
space when I go back? That's the question.
Right. So in category theory, we would say that these are adjunctions. If you don't know the definition of that, maybe it's not really worth going into. But we just kind of want to say when is this operation, like, when is it an inverse? When is this operation inverse of this operation? And there's an answer. And the answer is that it is an inverse for sober topological spaces,
Yeah.
which I can define. And what are called spatial locales. And I think it's worth talking about what these actually mean and how they fit into experimental domains. So I think the easier one is spatial locale. Spatial locale is one in which essentially equivalent statements, equivalent open sets are equal. So what do I mean by that? So if we have our notion of points, which are morphisms from 1 to X. So if for all X, which is a point, how do I say this? X is in S1 if and only if X is in S2. So S1 and S2 are elements of your locale. So they're open sets. There are statements. We're saying that for all points, these statements agree on those points. So the two, we'll say, two statements are equivalent if they have exactly the same points. Two open sets are equivalent if they have exactly the same points. This implies that S1 equals S2.
Okay, I need to break down this. So okay, so I don't have points, but I have morphism from 1 to X. And so I'm saying for all those morphisms, if X is in S1, so I don't know what that means. Is that in
Yeah, write that down.
okay.
So X is in S1 basically means that remember that a point, so we're thinking of points as morphisms from 1 to X.
Yep.
These are the same, this is the same thing as a selection or saying which open sets contain that point.
Yes.
So basically what this is saying is that if you think of X as a frame homomorphism, it's basically saying X of S1 equals true.
Yeah, but so I understand what X is my morphism. What is S1?
S1 is an element. So SI are elements of your locale or your frame, the opens of X.
Okay, but then I know. So here's the thing that I'm getting confused. So once in one sense, I say The object in the category, I don't know anything about its structure. I just know that it's a point and I have morphism. But now you're saying I know something about the structure because I know that it's a set of open sets.
Well, you can remember we can also recover. So you can think about this intrinsically or extrinsically. They're equivalent. But basically you can recover the open sets as maps into the Sierpinski space.
Okay, so then I have the map from 1 to x, and then the map from x to s.
Yeah.
And then what I'm basically saying,
So you
there
have
it
your
is.
map from 1 to x, your map from x to s.
Right.
And what we're saying is that s composed with x
Yeah.
equals the map from 1 to s that corresponds to 1. So you also have a map from 1 to s, which is
Exactly.
special, and we call it, what do we want to call it? Like true or 1 or something?
Oh, right, because that's just always going to be to map the 1 into 1. Okay,
Yeah.
right.
And what this is, like, if you wanted to define it in terms of morphisms, that's what this means.
So the point here is that this map is unique, right? Like
Which
you
map?
only have to, well, the one to S basically you only have one such map or something.
You have 2 such maps because
Okay.
the points of the Sierpinski space are 0 and 1,
Yeah. Okay.
but only 1 is verifiable. So there's only one open set corresponding to that.
Mhm.
Okay, so basically, like if I look at that one xs, so x you're choosing essentially a point, and s you're choosing an open set because the maps in correspond to the points, and the map out correspond to the open set, and then you're basically saying that if for all x I get s. If for all x,
So if it is the case,
yes.
this is the case. So if 2, I don't know what terminology, I guess I'll say open sets. If 2 open sets contain exactly the
It's
same,
the same points, I would say, okay, I got it. I
and
got
they're
it.
equal.
I got
This
it.
is like the axiom of extensionality in set theory, if you're
Yeah.
if you know that. But it's just saying that these are really, you can think of them as sets, right? Because in an arbitrary locale, you can have 2 elements of the locale, 2 open sets that have the same exact points, but are different elements.
Yeah.
Just because the notion of locale is very general. There actually exist locales that don't even have points. That there are no morphisms from 1 to x.
Oh, okay.
But this is saying that we can define, you know, we can actually think of them as sets of points.
Okay. So this is where then, so basically, okay, so we're saying that if I only had as a starting point the definition of the requirements of my verifiable statement that has that are closed under countable join and finite meet,
Yeah.
that would not be enough to be able to say I have points.
To say that you have a non-empty set of points. I mean, you always have a set of points. It just might be empty.
Right, yes.
But I think that for justification for that would be physical, is that, there is some true possibility.
Right. But that's kind of exactly. I structure the thing to start from the idea that I have underneath some type of Boolean algebra because I always need statements that are
Yeah.
true or false.
Yeah.
And what we're saying is that the locale would not give you that automatically. You would need an extra constraint to have it say that.
Yeah. I mean, if it's important that you have a non-empty set of points.
I think so. This is one other thing that I keep trying to do. I really, but then I can't I can't even set up even an abstract case where that I would be able to say that because again if I make the experimental test, like at least for that, I have the point. So you would basically say in that case, you wouldn't have the morphism, so you wouldn't have the incoming X's, but you still would have the S's that go out?
Yeah, because you could have some like I should have come up with an example of this, but yeah, it is possible to have like your definition is of open sets, but with no corresponding points. But essentially, like there's an action that you carry out in the book, which is to identify statements that are equivalent, that are
Yeah.
true on the same points. That corresponds to basically starting with your locale, going this way to topological spaces, and then
Yeah.
coming back. And so you end up with a spatial locale.
Yeah.
And if it turned out that your initial locale didn't have points, well, you're going to end up with a trivial locale. You're going to end up with the locale corresponding to the empty set.
Right. But so in
yeah.
principle, so does there exist a locale that has that I can think of finitely many elements of the poset that does not have points?
Finite. I will need to
Okay, you don't know if I ever heard, because I think well, we're going to talk about super spaces in a minute, but I thought that, for example, in sober spaces there are finitely many points, so then the space is automatically sober, the topological space.
That might be true.
Okay, so anyway, the point is,
I only know of like infinite.
yeah, because that's where the things become more
weird,
interesting, let's say. Okay, so but the point stands that in principle I could have a structure of locale with my joins and meets that I'm not gonna be able to find points defined as making morphism, and so the spatial locale is the one where essentially I can define points, and I can not only I can define the points, but I can then define every, let's say, every set of my poset as a set of points, elements of my poset as a set of points.
Yeah.
Okay.
And it means that if you start with a spatial locale, you turn it into a topological space and you prove something about that, and then you come back. These are really like these two categories here, spatial locales, sober topological spaces. These are equivalent, meaning that even the morphisms are one-to-one with each other. So really any statement you can just transfer back and forth.
Right. Okay, so let's talk about the sober topological spaces then.
Yeah. So these are so we have a topological space X, and if you have a closed set in X, that can be written as a union of really a finite union of other closed sets where the SI are strict subsets of S, because trivially, obviously, every closed set is itself, but a finite union of other closed sets, then we say that S is reducible. I don't know if it's I or A there. So basically a sober space, the closed irreducible subsets are in one-to-one correspondence with
the single. Okay.
So basically in this direction, you're taking the closure of the point. So we're saying that for every closed irreducible subset, there's exactly one point that it is the closure of.
So they don't need to be the singleton. They could be something else, but I still have a one-to-one map.
But if the space is T1 in addition, then it's just going to be the closure is the singleton.
Okay.
So I was trying to think of like a good like physical example of this, but like let's say you had a statement like, let's say you had n particles,
Yeah.
1 through n, and you say like one of the particles, at least one of the particles, has mass m, exactly m.
Mhm.
This is falsifiable. So it's a closed set. Is that clear?
Mhm.
Yeah, but it can be written as the finite disjunction of like particle.
Oh, if I have finitely many particles, yes.
Yeah.
Which can assume we have because yes.
Yeah. So you can write it as the disjunction of other closed sets.
Yeah.
So this would be reducible. Is that clear?
Yeah. I'm trying to. So I actually bumped into sober spaces like exactly this week because I was looking for something else that I realized that given two topological spaces, they might have the lattice of regular open set isomorphic as a Boolean algebra, but they are not the same space. And with the construction that I was doing, I was starting with the lattice of regular open set. So I said, okay, this is not going to work. So that sort of led me to a whole train of one of those. Oh, now this, and then I entered in sober spaces. So what I understood was the real difference is when you have just T0. And I also understood that there are subspaces that are not T0 and there are not T1, and there are
Yeah.
T1 spaces that are not sober, but all the T2, all the Hausdorffs are, yeah, there you go. As I was trying to understand where there are some T0 spaces that we're interested in that are not sober. That's the thing that I'm trying to understand.
Well, if you're starting from the locale, you're always going to get a sober topological space. So if you're taking a locale and applying this, the image of this arrow is sober spaces.
Yeah, so I'm trying to understand exactly because the construction that we do is sort of double dipping. So maybe you have a more understanding of the construction that we have than me. Because we start with a complete Boolean algebra.
Yeah.
And then inside the complete Boolean algebra, essentially embedded, there is a locale, a frame, I don't know even exactly how to go. Then you extract some elements of that, and then basically you see what remains attached. And you're saying that basically that's what we are doing. We are in that structure, we are extracting a locale and then going back and forth and recovering the points.
Yeah, so you're taking logical context, which is your complete Boolean algebra.
Yes.
You're finding the subset of that. That's the wrong name. That is verifiable statements. And so that gives you, just write verifiable statements. I don't know what you want to call the experimental domain, if it's the verifiable statements, if it's the space of possibilities, but so this gives you
it's the set of the experimental domain is a set of verifiable statements. So
okay.
that I think would be the thing that corresponds to a locale.
Okay. No, that would be the frame.
Okay.
So
okay.
This is a Boolean algebra.
Yeah.
This is a frame. And then like at some point you have to make the transition, like when you start wanting to consider like a space of possibilities equipped with verifiable statements.
Right. So basically from that I go then so if we say that the frame is experimental domain, then I have the sigma algebra, I have the theoretical domain.
Well, let's first go through the locale. So
Okay.
you get the corresponding locale, which I would call like the space of possibilities.
Right, but we do that after we have the
Yeah,
the
so this
theoretical
is
domain.
what I would do a little bit differently, but
Okay. Go
but
ahead. Do it differently.
like it's basically like I would want to forget the logical context as soon as possible. Like, I don't really want to, as like in math, like I wouldn't want to assume we're working in this ambient space of logical context. I would just want to get the verifiable statements and then build everything from that. It's equivalent though.
I'll let you go. Then I'll tell you what are the things that I couldn't do when I was trying to do that. So go ahead.
Yeah. So space of possibilities, this is a locale, which is really the same thing as the set of verifiable statements, just flipped. And because I believe it's in the logical context that you identify equivalent statements.
Yes.
So actually, this whole time we're dealing with, a spatial locale. And so this is the same thing as a Silbert space.
Okay.
So at this point, to be honest, you can forget that you're working with locale. You can just assume you're working with a topological space. And then what you do, and then you find the Borel sets basically of this.
So wait, before you go ahead, so you are saying that the fact that I have the equivalence of statements, that means that I have a sober space, and that means that all the closed sets are going to be so the points essentially. I have a map between the points of each experimental domain and the map and the irreducible closed set of that. So that there is an implication from I've taken that quotient to I have a sober space.
So I guess maybe there's a detail here that I may have missed. So you take the quotient among like possibilities in the logical context. You quotient by like equivalence of do you have a different name for it? Possibilities, is that the right?
So the possibilities, I only call them possibilities as when I have an experimental domain. Like before the experimental domain, I do not have possibilities. I have the possible assignments that are the assignment that I give to each. That basically, it's like they are the possible worlds or the what is it, model theory, or whatever they're called. But basically, they function that like they're possible ways that you can assign all the elements, and that's the first question that I have. Is I'm saying if two statements have the same possible assignment, they're equivalent.
Right.
And
So
that's one thing.
My concern is, what if you have, I didn't really think about this before, but what if you have points, like mathematical points, locale points that are just 1 to x, that are not corresponding to possible assignments?
I'm not good. So with the construction that I have, it's not going to be possible.
It isn't.
Right, because the fact that the Boolean algebra is complete, you can always create a statement that tells you, oh, I am in this assignment.
Okay.
Right, and that's basically what allows me to recover to make this essentially equivalence between statements and assignment. Like an assignment becomes a point. So the point is both a line in the table because it picks out a possible assignment, but then it's also a column, and it's the possibility I call the column that it's one only in that assignment, that is true only in that assignment.
Okay. Okay. Yeah. So if that's true, then quotienting out by the possible assignments means that if two statements have the same points, then they are equal.
Yes.
So then that means you have a spatial locale, and even if you didn't, once you turn it into a topological space, it would still be sober. Right. But because it is spatial, that means you can go back and forth.
So basically, what we're saying is that I should be able to prove, even going from locale or anything, with the construction that I have, I should be able to prove that the space is not just T0, but it's also sober. That's what we're saying.
Yes.
Okay, cool.
And that'll just follow automatically by construction.
Yeah, I understand that it would follow automatically, going through locale and so on, but I would also like to see the proof directly
Yeah.
in the
Yeah.
structure that I have, because then it tells me what's happening in the structure that I have directly.
Yeah. And basically the way that proof works is that you have your point of the locale.
Yeah.
Or well, now we're dealing with topological space, so
Yes.
maybe I should write this differently. But basically, if you have a frame homomorphism from the open sets of X to 2, the true and false truth values, this is going to correspond with irreducible closed sets.
Okay.
And then basically what you're trying to show is that these actually do correspond to real points in the topological space.
Yeah. Right. And I should basically be able to, yeah. So yeah, okay. I think I get it, because the idea is that I have my experimental domain. I'm making a subdomain with only one statement, essentially, with only one thing that can either be true or false, and then that I should be able to prove something from that. Okay. Okay, so that qualifies even more the spaces that we have. They're not just zero, they're also sober. Okay.
Yeah. So
So where are we?
yeah, I think I was just going to complete this diagram.
Yeah, go ahead.
With the sorry, what are they called? The Borel.
Yeah, the Borel algebra, the theoretical domain of theoretical
domain,
statements.
Yeah. So then you can take this and well, I guess this gets transformed. You take the Borel sets and you get the theoretical domain. Which is yeah. So it's a Boolean algebra.
The sigma algebra. So you have countable closure.
Yeah.
Yes.
What was I going to say about this? Oh, right, yeah. So the one thing I did want to point out, if we're good to kind of move on, or is there more we want to?
I'm good. I don't know if we went back and forth a lot, so I don't know if we lost the others.
No, it's fine.
Okay.
Yeah.
So the thing that caught me off guard while reading the book is the definition of inference relationship.
Okay. Well, it should be like the frame and the locale, right? The direction of the maps. Anyway, go ahead. Sorry, I mean to
Well, it caught me off guard because I thought it was a typo at first, but basically because it you have the map R between experimental domains.
Yep.
And then you're saying that R of a statement. Sorry, you have the map going the other direction.
Yeah, actually the Y and X.
You have a statement on Y, which is equivalent to the statement on Y. So the reason this caught me off guard is because you're comparing an element of the domain to the codomain.
Yeah.
But essentially the reason is because you're assuming there's like an ambient logical context.
That's exactly, yes.
Yeah. So that is fine. I mean, that can obviously be assumed. The one thing I wanted to ask about was like, does it have to be a logical context, or could you have like an ambient experimental domain?
I've wondered about that a lot. So one of the reasons why the context is more, because I want to be able to have arguments for people that posit things like hidden variables, parallel words, and all of those things. And all of those things need to be quotient out, right? Because they're gonna go away uh, when you take the experimental domain, because you're only going to take the sort of the experimental statement that it's the what is it? I call it the and that's another thing that I wouldn't need. But anyway, that it would be the narrowest, broader statement of that statement. So it's the one that it's the supremum, right? Is it the supremum? Yes, of inside the same lattice. And so the idea that I have, so that's one of the reasons why I keep it like that. Like in principle, you could say, well, let's just take all the verifiable strings that are there. Let's portion out all the things that are not experimentally distinguishable, and then probably we come with something that you might like more, right?
Yeah, and mainly it's because
So what is the problem that you are trying to solve? Like, why would that be a problem?
so the essentially because if we're restricting to being within like a single logical context, like you can define a category of experimental domains that all share a logical context. That
Okay.
is fine. But I think the morphisms of that category would be these inference relationships and not the like morphisms that we defined before. Because like the way I would think about this or describe it categorically, I think would
Yeah, go ahead.
be you have your two experimental domains, and we are thinking of these as frames.
Mm-hmm.
And they both are embedded in a larger, like this is why I want to say that it's the experimental domain, but I want to say there's like some, I don't know, omega.
Experimental context, let's call it like that.
Yeah. So I would want to say that it's also like a frame. And so these each like embed into the frame.
Right.
And then, well, what is an inference relationship? Well, it's exactly a frame homomorphism that where this diagram commutes.
Right.
So that's what I would want to say. And then you could even take a category of like the frames that are included into this frame.
Yeah. So there are a couple of things that are sort of evolved, and I still don't know whether I have. So if I were able to do that, I would have to really say that the whole context has essentially a countable basis of experimental of a verifiable statement. I do not know that I'm ready to do that because I don't like. I don't know whether that's necessarily true. So could it be that there are uncountably many, but whenever I do something, I actually restricting to the countable things that I have. And I quite frankly don't know whether I don't know whether is important because you might even be able to say, oh yeah, but for some reason that I don't know, it wouldn't matter anyway. So you're trying to worry about a problem that doesn't exist. Or I don't know whether the problem can exist, and if it can exist, whether it's relevant or not for experimental verification or not.
I
So
see.
These are elements where I was not ready to commit. The other thing that I also do not know how to do it right now, it's a little bit kludgy, is when I do the space of possible maps of possible relationship. And there the idea is that essentially it's a possible relationship essentially exists in its own context. And so right now, I have maps from context to context that basically say, there are many contexts that are possible, and then I have the sort of meta context that tells me, how do I choose and how do I verify where I'm in one context or the other. And in principle, it may be that you can make just that each context is like a separate set, of possible statements in the bigger context, and you're just conditioning and getting things out. But I don't know, again, if that's general enough and covers everything. And because one of the problem is that whenever we set up a different experiment, we do have different contexts because we do have different definitions and different presupposing assumptions and so on. So typical example, if I am trying to verify special relativity and I want to know if the Doppler effect exists, I have to be agnostic of whether it exists or not, because it's the experimental verifiable statement that tells me whether I have it or not. But when I am building a radar that tells me the velocity, then I'm assuming that the Doppler effect exists and it has some. And so those are the pieces that I quite frankly don't feel solid enough to make a statement that say, okay, yeah, this is gonna cover everything. Because then to be able to make this general statement, I have to basically be sure, yeah, it's gonna cover everything.
Yeah, that makes sense. The other thing I was going to point out, like related to that, is just I think you've probably kind of already addressed this with what you said, but like if you want verifiable statements, mod equivalence, which is exactly the experimental domain,
Right.
that this is the same thing as there might be a subtlety here, but experiments mod equivalence.
What do you mean?
So an experiment we would define as like a physical process that returns success or failure or runs forever. And then we would say that two experiments are equivalent. So P1 is equivalent to P2 if they return success in all the same cases.
Right.
Yeah, makes sense.
And there's a mapping back and forth, because you can take any verifiable statement, by definition has an experiment that succeeds if and only if the statement is true.
Yeah.
And in the reverse direction, you can take an experiment and just say like E succeeds.
Yes. So what is the question?
So I guess like this maybe suggests like a way to skip the logical context and just say like an experimental domain is a domain in which you can do experiments, and that the corresponding frame is just the experiment's mod equivalence.
The problem with that, so in original incarnation, I was trying to be a little bit more specific and bring the experimental in as object in the framework. The problem is it becomes horribly complicated to even say what an experiment is and how do you actually combine tests and so on. And so the choice was to basically punt on trying to formal, because one of the things that we want to have is that whenever we make a definition, I want to have a little bit of description of what that definition maps in terms of, and then. So the fact that I have the verifiable statement defined, but not the experiment, it allows me to not be so thorough in trying to define what the experiments actually are, and also leave the experiments as things in a sense that might not really, like, I can say, factually exist in reality, because it says they're basically complete idealization. And since the statement themselves are already this type of idealization, then I'd rather just talk about the statements. And in some sense, it makes it closer to. So I understand that there are different ways to look at these things. And one other thing that I need to do, especially for the basic definition, is to have things that are closer in the way that like a physicist and engineer, especially an experimentalist, would think about things. And the experiments, the measurements, and so on, they're already fraught with so much baggage, and the statements are not, that I'd rather talk about statements, like really tactically. If I started my work and saying, oh, there are experiments, I would be like completely bogged down into, oh, but what is an experiment? Oh, what about quantum mechanics? And what about this? So there is also that sociological aspect that I'm really trying to avoid.
That's really interesting because I think it's just our different backgrounds. I had like the opposite experience. It's like for me, a statement has a lot of baggage, like philosophically, like how do you say something objective about reality? Whereas an experiment seems a little bit more concrete. It's like something you can actually like do and see a number on a screen. And
Right. So that's why the verifiable statement is sort of nice because cuts
yeah,
cuts in between. Yeah, it's a statement, but it's one where we have an experiment, right?
yeah,
Yeah. And even there for statements, I go to great length to say it's not a propositional statement. Like I don't have a grammar, I don't
right.
have a predicate, and so on, because even that it just fails. I mean, there have been attempts, for people to try to do those things. They just don't work. And this is where I did collaborate a little bit with the philosophers. I like, especially the first few sections of the part that you read. We went through them with a few philosophers until they had, yeah, okay, uncomfortable with this. So,
Cool.
yeah, there are like in all these choices, there are like a lot of there are reasons, but either if I had to write all the reasons, it's like I'm opening the can of worms, and I don't want to open the can of worms. I want you to be focused on the construction that we do later. So
Yeah, yeah. So yeah, I thought it was very well constructed. I didn't really have like a philosophical problem with how it went. I just was wondering if bypassing that part made sense. But
no,
yeah,
very good, very good. Like no, you did a splendid job. And as I said, the more people that read through it, and the more it gets validated. That's why I'm trying to be very open because it touches so many different things that it needs to be looked really by many people.
yeah,
To see what, yeah. So, but conceptually, I agree that I have something like that in the back of my head. I
okay.
just don't want it declared in the construction. And somebody can go ahead and do it on the side, but I don't want to. It's even why I am, I have this very awkward way of defining statements and then recover that they're Boolean algebra instead of setting that it's a Boolean algebra. And some mathematician tells me, well, why don't you just set that you have a Boolean algebra? The problem is that I need to justify that I have a Boolean algebra, and then I have like what are like 16 the properties that I have to verify. Like it's instead on the other side, I can be like much thinner in the axiom that I'm giving, and I'd rather do that.
Mhm.
So
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 yeah, I think that's all the topics I had that I wanted to
so
cover.
regarding all this, I have another question that probably this thing you might be more equipped. So again, we have this fact that, as you said, we are embedded in something bigger. So even when we do the combined domain, which basically would be your product in category term, like it's like how can I say? It seems to me that because this is in an ambient structure, when you're doing the product, the ambient structure basically tells you what type of product you have. Like that's basically the idea. So if I have two variables, right, a temperature of my mercury thermometer and my height of the column, right? When I'm trying to put these two elements together, there is the ambient structure that tells me, yeah, one fixes the other. These things are not, and uh, and so I think like one of the things that we looked with some other mathematician at some time, it would basically, if we try to define the morphism in that category, basically the product and the coproduct become the same thing. Does that make sense to you?
Yeah, that happens in some categories.
Okay.
I think it might be called linear categories or something like that, or it just happens in like abelian categories as well.
And then
Um,
the question that I don't know how to sort of even ask at this point. So suppose that I have two domains, right? I could have a bunch of different products or way to combine this domain depending on the ambient space.
yeah.
What are all the possible maps or relationship that I can have based on all the possible ambient spaces? Like that's the question that I still don't know how to answer.
Yeah, so for me right now I see two. I see if you are assuming a shared logical context, or that they're embedded in something larger where you can compare statements between them,
Yeah.
then inference relationship seems to be like this commuting diagram, which is the same thing as an inference relationship. That is a notion of morphism. I didn't work out the details, but I think that probably if you took the product in that category, you would get your product. I don't know if you've verified that. And then you can also assume like, or not assume that there is this shared logical context, that you're just taking like arbitrary experimental domains and taking mappings between them. And I think so I think earlier I was talking about like a thermometer, like measuring a system. Like the thermometer system exists as like a mathematical entity. And so it doesn't have like an objectively true, well, I guess if you're thinking of it as a single thermometer in the real
I'm thinking as a single thermometer, yes.
then it does have a particular temperature that it's at.
Exactly.
But if you think of it as a like an abstract object that can measure temperature, then you could have mappings from different systems that give different temperatures.
Right. So that's a problem when I started, I wanted to construct essentially state spaces and systems, because there needs to be a way to have the specific ones, right? Where I have this particular system at this particular time making this, because the verifiable statement can only be of that type. Because the verifiable statement has to be this, and I'm using this test. But then there has to be a way to abstract that, because you need to say, okay, for even just the same system at different times. But then it means that the statements are parameterized by something else. So I have the temperature is between 24 and 25 Celsius at time t, and that's a verifiable statement. So at time t1, and that's another statement, right? And that part I haven't like completely fleshed out, because there has to be some kind of the idea I have patterns, and then with these patterns get instantiated in different experimental domains, and then these things have actual relationships.
Well, you do define, like when you define properties, you define that as a continuous map, right? Between
Yes.
or experimental domain, or sorry, the space and another topological space.
Okay.
So that to me, when you're thinking of them as topological spaces with continuous maps between them, that to me is the abstract version that doesn't have a shared logical context.
You are absolutely right. I I didn't see it. That's what I was saying before. You have you have different circuits in your brain that gets triggered in different way. Yeah, you're right. So the sort of the state space or whatever we're going to call it, this pattern is the fact that I can map back and forth in another space as a topological space. But then when I make the experiment, I then link to the okay. Interesting. I have to think about it. And so at that point, then I would have, again, this more abstract thing, the fact that then I have a different experimental domain, they all map, and then I can have like these products, this combined domain with all the other pairs that are also mapped from another way, and then I can say, okay, in this case, I have one type of product. So if I have the thermometer and the height. If they are all the same thermometer, then the two are linked, and therefore they're basically the same domain. If they are from two different things, then I would have the topological product between the two, because the two things are. Okay. Well, this was tremendously useful.
I'm glad.
I don't know if there are other people that have questions, or if you have other questions and comments.
Probably not. That's worth getting into.
So we are at the half hour, so we should probably so thank you so much. I don't know how to thank you. And so I don't know if there are other pieces that are of the projects that are sort of in the realm. So that, yeah, so I don't know what other parts of the project are going to be interesting to you, because the other parts are about more on the physics end.
Yeah.
A lot of the other stuff where we have been working out in the past lives are more on. So there's always the part of topological spaces, but there's also going to be a part of convex spaces, being able to define an entropy and then figuring out how much we can get from the entropy, and connection to analysis, because then we have to be able to represent these as either measure theoretic structure or elements in function spaces, and so there is all that part, but it might not be the part that you have experience on, I assume.
Right. I don't think I have experience on any of that. I'm happy to take a look. I'll maybe look through the recent additions to the book, if that's the right place.
Well, so there is let's see what is very interesting to you. There is the whole part of so the part that is in the actual sections, like in the physical mathematics section, that's the part that I sort of consider done for some definition of done. That means it's good enough that I can go and work on other things. And then in the last section, there is the sort of some of the experimental part that we're working on, and there is a whole chapter of ensemble spaces. And that's the part that I am actually working on right now. And it's a little bit more constructive in the sense that, one of the problems that I have with category theory is that at the end of the day, I need to talk about the objects, because that's what I can define in. And so the category theory is nice because you can see the structure, the mathematical structure. But at the end of the day, when it's like I'm trying to figure out what is the correct category for physics in some sense. And so the fact of studying relationship with with categories is not going to help me find the correct category. I don't know if it makes sense. Like so the category theory allows you to sort of see a deep connection between things that are that are living in different, that seem to be living in different space, in areas of math, and actually they're not. And there is a part that is gonna. So the part of the ensemble spaces, we're trying to find some kind of nucleus that then we can show that all the other things that we do in physics, like differential topology or measure theory, or that all the structure are basically reformulation, hopefully, of this core structure that we are doing. So I have a sense that maybe category theory might be good for that, because then they're all functors for one thing or the other. Then, of course, part of the problem is finding what are the correct factors and finding the correct category. So even there, I don't know how much, but then maybe somebody has a bigger sense of what possible things are there. So anyway, I don't know whatever parts might be interesting to you. And I know, so another thing that I know in terms of morphism that I would basically need in this basic structure is some kind of a type of projection where you can go map from one domain to the other, and there should be the map of finding essentially you map to the supremum, which basically mean you are removing information from going from one experimental domain to the other. So it could be that that you have position in X and Y, and then you map to the domain of only X, right? You are basically doing a projection in that sense. You're taking a subset and then you map on that and remain that. And I think there is going to be a relationship between the projection of the statements and the actual projection that you do in vector spaces and all that. So I always thought that there should be a structure there. They should be the same, but I haven't worked that out. And it's one of the problems that I only have finitely many hours in a day, and I have to choose which. So in principle, what I'm saying is that in principle, there are other parts that needs to be like better understood. It's just that my attention is not there at all. So
Okay. Well, I can take a look, and I don't, have a lot of time to dedicate to this, but
exactly. Yeah.
I
So
can.
anyway, this was already like super useful. So thank you so much for taking the time to look at the book, and and mapping the terminology. So I think I have a much better understanding of what. So basically, to recap, a frame is where I'm thinking of the open sets as the important thing. So when I'm thinking of match between open sets to open sets, I should be thinking in terms of frames. Locale when I'm thinking in terms of points. And then there is this issue about superspace and special locale. So it was a more specific category that I had to look at, and not just that. So I think in an hour we sort of cleared out the doubts that I had for years. So this has been very, very useful to me. So thank you again.
I'm glad.
Okay, so if there are no other questions, then we are just gonna end and see you next week. Bye.
Yeah, see you. Bye.